Hi everyone, welcome to this wonderful session. Today in physics, I am going to start a new chapter which is motion in a plane. In this chapter, we will elaborate all the concepts we have learned in motion along a straight line. तो शुरू करें?
Motion in a plane. Generally, what we see around us that objects do not move in a straight line, rather they move in a plane. And if we have to analyze that kind of motion that is in a plane, then we have to take help of vector. So I think I can assume that you must be familiar with vector operations. So assuming this, now I can start. How motion can be analyzed? Again, it has to be with the help of some kinematical terms as we had discussed for one-dimensional motion. So let us start with position vector and displacement. But here motion is in two dimension. So let us denote this coordinate axis y and x. If one object is here, it has to be a point object, of course. Let this is here at point P1 and then move to point P2, right? Here you can see motion is not only along x, not only along y, rather this is in the plane xy. So if we locate position of first point P1, then this can be written as position vector of P1. I am representing here by R1. And let us again, if we draw position vector for P2, let that be R2. Here R1 and R2 are position vectors of points P1 and P2. Now the particle has moved from P1 to P2. So this must be the displacement vector. What is displacement vector? I think you can recall now. Displacement vector is final position minus initial position, which is irrespective of the choice of reference. Here I had taken reference as origin. And this delta r should be independent of where we are taking this reference. It can be here or anywhere we can take the reference. Delta r has to be same because it has nothing to do with what was initial or final position vector from a particular point. The only difference between these two vectors will give the displacement vector delta r. So now we can write r1 can be written as, in rectangular component form, it can be written as x1i plus y1j. You all must be familiar with this kind of notation, which is vector representation in component form. And similarly, r2 can be written as x2i plus y2j. So if we are interested in final position minus initial position, that is the displacement vector r2 minus r1. This is delta r. It can be written as x2 minus x1i plus y2 minus y1j. So this is how displacement vector can be written in rectangular component form. Now I am moving to next kinematical term, which is velocity. Here again, as in the case of one-dimensional motion, it is average velocity and instantaneous velocity. Now I think you will recall all these definitions. What is average velocity? It has to be net displacement upon net time for the whole time of journey, for the whole time span. Whereas instantaneous is, it is velocity at some particular instant. So average velocity, if we write vectorially, that will be equal to V can be written as delta r upon delta t in vector form. But do remember here these vectors are not only along a straight line. So always we have to use its component form representation, which can be written as Vxi plus Vyj. Now what is Vx and Vy? Vx is x component of velocity and Vy is y component of velocity. Individually these can be written as, Vx can be written as delta x upon delta t and Vy as delta y upon delta t. Here one interesting question comes, whether these components are scalar or a vector. That I had written Vx and Vy, so whether these are scalar or vector. as you all must be knowing that components we get with the help of dot product of vector with unit vector along the direction in which we have to take the component. So since it comes from the dot product of two vectors, so it has to be a scalar. Also we can say logically that already direction is specified while writing the component, because when we are saying Vx, so direction is specified that we are taking component along x-axis. So why is it needed again to write the vector? So these components are a scalar terms. So it is how Vx and Vy is written. Next is instantaneous velocity. As we all know now, V can be written as dr by dt, because we have to take here very small differential displacement, that is dr, in a very small differential time, which is dt. So it is written as dr by dt. Similarly here we can write, if we are interested in rectangular component, because always rectangular component will be more helpful while solving numericals. So V should be written as Vxi plus Vyj, in which Vx is dx upon dt. Do remember this is a scalar quantity, and Vy is dy upon dt. So we have to differentiate position variation with respect to time to get the instantaneous velocity term. Now what is direction of instantaneous velocity or direction of average velocity? As you can see, it has to be along the direction of displacement, not along the direction of position. It has to be along displacement, because this is defined as displacement upon time. Next kinematical term that comes in our mind is acceleration. Now acceleration, as we all know, is rate of change of velocity. Again, we can categorize this into average and instantaneous acceleration. What is average acceleration? Average acceleration can be written as change in velocity, the same we are writing as in 1D motion, with only difference that here we have to write mostly in rectangular component form, and this vector sign is very much needed now. Here we cannot simply omit vector sign and then write plus and minus, because kinematical terms are in 2 dimensions. So here it is to be strictly written. A is written as average acceleration as delta V upon delta t. Now if we write in rectangular component form, then it can be represented as delta Vx upon delta ti plus delta Vy upon delta tj. So this is net change in x component of velocity upon time plus net change in y component of velocity upon time. The same is for instantaneous acceleration, which is dv upon dt. If we write in rectangular component form, that would be dvx by dt I plus dvy by dtj. Again, do remember that direction of acceleration has to be along change in velocity, not along the velocity. So this must be clearly understood, because generally students make mistake here while writing direction of acceleration. Here it won't be along velocity or opposite to it. That is in the case of one-dimensional motion. But here you have to write the direction as well. So let this be initial velocity, this be final velocity. We have to write direction of delta V. What it will be? It will be in this direction. If you see it according to vector rule of algebra, then V2 minus V1 is equal to V21, that is change in velocity. And if we write V2, it will be equal to delta V plus V1, which you can see is satisfied in the above vector triangle. V1 plus delta V is giving you the resultant V2. So this is direction of acceleration. If we have to write only the magnitude, so how it will be written? Magnitude of A can be written as square root of ax square plus ay square. Like any rectangular component, we can write the magnitude as square root of x component square plus y component square. Now just to illustrate these things, I have selected some example. In first example, the position of a particle is expressed as r is given here, position vector is given, that is 4t square I plus 2tj. Find the velocity of the particle at t is equal to 3 seconds. Now we know the relation v can be written as dr by dt, and it is written here in its component form, so it has to be d by dt of 4t square, which is along x direction. So I to be written here plus d by dt of 2t, and again the direction is written as j. On differentiation it will give 8ti plus 2j. So this is expression of velocity we got. Now we have to calculate velocity of particle at t is equal to 3 seconds. So velocity at 3 seconds would be 8 into 3, that is 24i plus 2j. So magnitude of velocity has to be written as, now we know how magnitude is calculated. This is square of x component, which is 24 square, plus square of y component, which is 4. So if you add these two values, it will come out as 580. That is equal to 24.08 meter per second. This is the magnitude of velocity. But as we all know, velocity is a vector quantity. So magnitude we have calculated. What about the direction now? Direction also to be written. So if this velocity is making some angle theta with x-axis, let this angle be theta, then tan theta can be written as y component of velocity upon x component of velocity, which is 2 upon 24, that is equal to 1 by 12, and theta we got tan inverse 1 upon 12. This is the angle velocity vector is making with x direction. Now I am considering, this is again 2D motion but with constant acceleration. As you can see here, it is motion in a plane with constant acceleration. If acceleration is constant, of course we can write all the kinematical expressions that we use for constant acceleration. Let us start with first one, that will be v is equal to u plus at. Of course it can be written here directly for 2D motion. Later we will see how this can be directly used in numerical examples also. So v we can write as u plus at. Do remember that here this v, u and a, these are not along a same line. They can be in different directions. The next one is s is equal to ut plus half at square. Again I have written the vector sign here, so it can be applied directly to 2D motion also. S, u and a all can be in different directions because here motion is in a plane. The third one is very interesting, which is v square is equal to u square plus 2as. In last chapter also I had discussed that here we cannot put the vector sign. There is no square of vector thing. So it has to be written in projection form. Now if we have to apply this equation for 2D motion, it cannot be applied directly for the entire motion. It has to be written along x direction and then written separately along y direction. Then on combining the result along x and y axis, we will get final result. So this only has to be written separately in component form. Otherwise equation 1 and 2 directly can be applied for the 2D situations. Again I think we should take some numerical examples so that these things which we learned will be clarified properly. So let us see some examples. The first example is an object has a velocity at time t is equal to 0. Okay, so this is the initial velocity given here. U is 2i plus 4j. I have written u, so already it is specifying that this velocity is for time t is equal to 0. It is undergoing a constant acceleration. Acceleration is provided here, which is I minus 3g. and this acceleration is only for 4 seconds. First, it is asking find coordinates of the object if it is at origin at t is equal to 0. So, original position is r0 if we write the initial position, that is equal to 0 at t is equal to 0. Okay, so which equation we should use? It is asking coordinates of object at the end of 4 seconds. So, we should write s is equal to ut plus half at square. Now you will see how directly vector equation can be written even in case of 2D motion. So let us write directly the vector equation. I am writing position at t is equal to 4 seconds. So that can be represented as r4. So that has to be equal to ut and t has to be 4 plus half at square. And again square of 4, that is 16. Now if you solve this and substitute the values of u and a, we will get 4 times 2i plus 4j plus 8 times I minus 3j. That will be equal to 8i plus 16j plus 8i minus 24j, which is equal to 16i minus 8j. So this is position at t is equal to 4 seconds. There is no need to subtract the position at t is equal to 0 because that value is already given as 0. It has started motion from the origin. So this is position of particle at t is equal to 4 seconds. Now if we have to write the coordinates, that will be equal to x coordinate will be 16 and y coordinate will be minus of 8. So these are the coordinates at t is equal to 4 seconds. Now come to this second part in which it is asking magnitude of velocity at the end of 4 seconds. Okay, this I am solving here separately. Magnitude of velocity at the end of 4 seconds. So v4 can be written as, just put the value of 4 in place of t. So that will be equal to u plus at can be written here. So this is u plus a and t is 4. So write here 4a. That will be equal to 2i plus 4j plus 4 times a is given I minus 3j, which is 2i plus 4j plus 4i minus 12j. That will give us 6i minus 8j. This is the velocity in vector form, and if we are interested in its magnitude, that can be written as square root of 6 square plus 8 square, which is 36 plus 64. This comes out to be 10 meter per second. What about its direction? Again, in the same manner we had calculated for position, this can be written as tan theta is equal to Vy upon Vx, which is minus 8 upon 6. So this is how theta can be written. Theta will be equal to tan inverse minus 8 upon 6. Finally, we got velocity at the end of 4 seconds and coordinates of object at the end of 4 seconds. One very interesting condition I have: find the time after which velocity vector becomes perpendicular to initial velocity vector in a projectile motion. Though we have not yet started the projectile motion, but still we can check after what time velocity will be perpendicular to initial velocity with the help of vector analysis. Now, whenever it is said that angle between two vector is 90 degree, the first thing that should come in mind is that dot product of the vector should be equal to 0. So, if we have to write velocity is perpendicular to initial velocity, directly it can be written as v dot u is equal to 0. If I draw projectile motion, you all are familiar with this kind of motion. This is the initial projection velocity and it is the angle of projection. As you know, g always has to be vertically downward. Now we have to write v in vector form. What it should be? As we know that v is equal to u plus at directly can be written in vector form even for 2D motion. So in place of v, we can write u plus gt. The acceleration here is g. So this is u plus gt dot u, that is equal to 0. Now if you take dot product, u dot u will be u square plus this is u dot gt. So it can be written as u gt and cos of angle between the vectors u and g. Now from the diagram you can see what is angle between vectors u and g, that is 90 plus theta. So it should be written as cos 90 plus theta, and this is equal to 0. What is cos 90 plus theta now? That can be written minus sin theta. So this is u square minus u gt sin theta, and it should be equal to 0. From here we can write t is equal to u upon g sin theta. So this is the time after which velocity vector becomes perpendicular to initial velocity vector. It is very beautiful representation of how vector analysis directly can be used in case of any situation whenever it is given that a given vector is perpendicular to another vector. So directly we can apply equation of kinematics in vector form if it is a 2D or even if it is a 3D motion.
Let us solve one example more. A helicopter is flying horizontally at 8 meters per second at an altitude 180 meter. When a package of emergency medical supplies is rejected horizontally backward with a speed of 12 meters per second relative to the helicopter. Here the velocity is given, that is relative to helicopter. Ignoring air resistance, what is horizontal distance between the package and the helicopter when the package hits the ground? So let us solve this example and then see which of the given option is correct. From this given data, we can calculate time taken by package to reach the ground. So t can be calculated if t is the time of flight, that is the time taken to reach the ground, that will be equal to, it has to be 2u by g under root. Now on substituting all the numerical values that is provided here, it will be 2 into 180 upon 10. On solving this, we will get 6 seconds. So 6 seconds is the time in which the package reaches the ground. Now in this time, what is horizontal distance that is travelled by helicopter? Let that be S1. So S1 can be written as equal to, as the helicopter is flying horizontally with constant speed, so we can directly get value of S1, that will be 8 multiplied with t. So its value will be 48 meter. And in the same time t, the distance travelled in horizontal direction by package will be, let's say S2. So S2 has to be equal to, now we have to write velocity of package in horizontal direction. Here relative velocity is given. So first calculate the velocity of package, that will be velocity of package with respect to helicopter, which is 12, plus velocity of helicopter. But the package has been thrown in backward direction. So if 12 is written with positive sign, negative sign has to be for velocity of helicopter. They are in opposite direction. So this value will be equal to 4 multiplied with t. On substituting value of t, that is will be 64 meter. And they have displaced in different directions, in opposite directions. So separation between the helicopter and the package, that is delta S, will be equal to S1 plus S2. On substituting these two values, it will be 48 plus 24, which is equal to 72 meter, which is our option number D. That is the desired result.
With this, today's session is complete. We got introduction of projectile motion. In the next session, we will learn some problems based on these all concepts we got to know today about, and then we'll move further. Also do remember that this topic is very important from NEET and JEE point of view, so you have to practice more and more questions from the topic. So please keep practicing and keep revising the concepts. for your preparation. It's a good luck. Goodbye.